Now we're going to do a simulation in R to find the statistical power of detecting a difference between infected and non-infected chickens. So let's start with a sample size of 20. Now we're going to simulate a population of non-infected chickens. And we do that with the code RNorm, which means that this is a normally distributed population with a mean of 50 and a standard deviation of 10. And from this population, we take a sample of the size we decided here, 20. So now we have a sample of 20 from simulated population with a mean of 50 and a standard deviation of 10. That is our non-infected chickens. And we do the same for the infected population. We simulate a population with a mean of 40 and a standard deviation of 10. And we take a sample of 20 from these infected populations. And now we join these two samples into one single vector. And we also add labels so that we know which birds are infected and which simulated birds are not infected. And the first 20 are non-infected and the last 20 are infected. So now let's make a plot over this. And we see here in the plot that it looks like the infected birds are smaller than the non-infected birds. And that is exactly what we would expect, of course, because we know that the truth is that there is a difference between the populations. However, just by chance, we could have sampled the smallest non-infected birds and the biggest infected birds. And just by chance, we would have missed this true difference. And that is, we would have made a beta error. Now, let's do a statistical test. And we start by making an ANOVA, something that we're used to. And here you see that the difference between these samples is significant. So here we did detect the true difference. We did not make a beta error. So that was good. But we can ask ourselves, how often would we be this lucky? If we did this 1,000 times, how many times will we draw the correct conclusion? That is, reject the false null hypothesis and get a p-value that is below 5%. In real life, you can never do an experiment 1,000 times, but luckily in a computer, you can. And that is what we will do now. So here comes some explanation of how the codes work for this simulation. First, we create an empty vector, that is an empty box. And here we will put the results from our 1,000 tests. And then we tell R to do something 1,000 times. And what exactly? Well, exactly what we did earlier. We take samples of 20 from two populations, one with a mean of 50 and a standard deviation of 10, and the other one with a mean of 40 and a standard deviation of 10. And we test the difference between these two samples, and here we pull out the p-value from that test and put it in the empty vector. And we do this 1,000 times. We make 1,000 statistical tests. Now let's have a look at this vector that was empty in the beginning. It is now filled with a list of p-values from 1,000 tests. And as you see, these p-values differ a little bit from each other, just by chance. So, okay, we know that there was a true difference between our populations, but how often did our statistical test detect this true difference? That is, how often did we get a p-value that was under 5%? Well, we got this 858 times out of 1,000. That is, in 85.8% of the times, we rejected the null hypothesis, which was false. We correctly rejected it. And this is our statistical power. We have an 86% chance to reject a false null hypothesis. That means, of course, that in about 14% of the times, just by chance, we would not have detected this difference between the samples. So, can we improve our power? What happens if we increase our sample size to 40 instead of 20? We do the same things. We create two populations, we take samples from them, now with a sample size 40. We make a statistical test between the samples, and we do this 1,000 times. And this time, we detected the true difference 99.3% of the times. That is an extremely high power. Let's just see what happens if we would have a smaller sample size. A sample size of 10, for example. We do the same thing again. And with a sample size of 10, we detected the true difference only about 56% of the times. So we see here clearly the sample size highly affects the chances of detecting true differences. Sample size increases our statistical power. And generally, we would say that a power of 80% is good.